Welcome to Lesson 3 of the Physics 30 Prep Fast Track. In this lesson we'll look at speed and velocity and position time graphs. Speed and velocity are often used to describe the same thing, but there is an important difference between them. First, to define them, speed is found by measuring the distance traveled and dividing that distance by the time taken for travel. So speed is distance over time. We often see the formula written S is equal to d over t. In physics, we usually use V is equal to d over t. The V stands for speed, or the V can also stand for velocity. Velocity is found by measuring the displacement and dividing the displacement by the time taken for travel. And so it's essentially the same formula, only instead of the d standing for distance, it stands for displacement. Now you can see that we have drawn a little arrow above the v in the velocity equation. The little arrow indicates direction. All right. Notice that in the speed equation there is no arrow. There is no direction given. But in the velocity equation, there is an arrow over the velocity. There's also an arrow over the displacement, and we'll explain that in just a moment. But the equations are basically the same form. V is equal to d over t, and V can stand for both speed and velocity. Let's look at some examples of how they are similar and how they are different. So the big difference between speed and velocity comes from the difference between distance and distance. Distance is a scalar. Scalars have no direction. Time and money are examples of scalars. Money cannot have direction. Temperature is another example of a scalar. You can have a positive or a negative temperature, but you can't have a temperature that's 15 degrees north, or you can't have $20 southwest. All right. However, displacement can be a vector. All right. Distance could also have direction, but then it would be displacement. So basically, when we say distance, it doesn't have a specific direction, but can be in any direction. Whereas displacement must have a definite and defined direction. So since speed is equal to distance over time, then speed is a scalar value as well. So speed and distance are scalars, whereas velocity and displacement are vectors. Vector, that means it must have direction. Notice for speed, distance over time, velocity, displacement over time. Now you understand what the arrows are all about. So probably the best way to understand the difference between speed and velocity is to look at a couple of examples. So we'll look at three straightforward examples. Example number 1, a person walks 3 meters east and then walks 7 meters east. The first part of his motion takes 5 seconds. The second part takes 5 seconds. What's the speed? What's the velocity? It always helps in physics to draw a diagram to help you visualize these events. And of course, when you draw this diagram, you sometimes need a frame of reference. And so the little compass on here is actually telling us that north is to the top of the page, south is to the bottom, east to the right, and west to left. 3 meters east, I would draw a short arrow that is going towards the east, and then add to that a longer arrow of 7 meters. All right, also to the east or to the right. And the resultant of these two vectors is, as you can see, 3 plus 7 is 10 meters. So the total distance is 10 meters. Also, though, the total displacement is 10 meters, but you also have to say with displacement what the direction is, and of course it's to the east. So when we calculate the speed, speed is equal to d over t. Distance over time is 3 plus 7 meters over 5 plus 5 seconds, 10 meters in 10 seconds. Velocity, however, is 3 meters east plus 7 meters east gives me a total of 10 meters east in 10 seconds, 1.0 meters per second east. Now notice that they both have the same magnitude, that is 1.0 meters per second. But velocity must also include the direction, and this is very important in the next example, which is not quite as uniform as this first example. In example number 2, the same person, instead of walking 3 meters east to begin with, walks 3 meters west, then turns around and walks 7 meters east in 5 seconds. In this case, what's the speed? What's the velocity? Again, drawing a picture helps. Notice in this case, using our compass, 3 meters west represents 3 meters to the left of the page. And of course, when we draw the next vector, we should draw that next vector from the end of the first. All right, so where the tip of the arrow is, that's where we put the foot of the second arrow, and the 7 meters east goes to the right. But of course, what's our distance? What's our displacement? What's our speed? What's our velocity? The vector sum of these two vectors, 3 meters west and 7 meters east, is only 4 meters east. So when we calculate the speed and velocity, we have to keep in mind that the distance, which is 10 meters, is different than the displacement, which is only 4 meters east. So as you can this first calculation is a distance over time, 3 plus 7 again, over 5 plus 5 again, 10 over 10 equals 1.0 meters per second. On the bottom, we've got 3 plus 7, but the 3 is to the west, the 7 is to the east, and so one of them has to be made negative. And this is an arbitrary decision on your part, which one should be positive and negative. Generally, we make east and north positive, south and west are negative, but you don't have to do that. It's just a sort of a conventional approach. However, negative 3 plus positive 7 gives you positive 4. The positive being east means we went a total of 4 meters east in 10 seconds, giving us a velocity of positive 5 meters per second, or in other words, 0.25 meters per second east. And of course, there's your total distance. There's your total displacement. To find the speed, we take distance over time. To find the velocity, we take displacement over time. And of course, as I mentioned, the 0.25 positive means east because we arbitrarily assigned east as a positive and west as a negative. Our third example is a little more complicated because it's not just east and west, but we have a two-dimensional type of motion here. A person walks, again, 3 meters north in 5 seconds, then turns and walks 7 meters east. So similar two examples, but this time he first walks north, so let's draw a picture of that. 3 meters north, as you can see, north is to the top of the page, and then from the tip of the first vector we add the boot or the foot of the second vector, and so we have 3 meters north, 7 meters east. The distance traveled is 10 meters. The displacement is from where we started at the bottom of the blue vector to where we end up at the right of the red vector. And so our displacement is an arrow that's drawn from the start to the finish. And as you are aware from your studies in math, that distance is not going to be 10 meters, but is going to be a little bit shorter. And you know that distance is called the hypotenuse. So what we would have to do is figure out what length depth of that hypotenuse is. And using some simple Pythagoras, all right, c squared is equal to a squared plus b squared. We get 3 squared plus 7 squared. 9 plus 49 is 58. So c squared is 58. C is the square root of 58, or approximately 7.62 meters. All right, that's the displacement of the person, but of course, displacement is a vector. Vectors must have direction. So we need to find out what the angle is, and I've done a little bit of a calculation here. We can see the speed is still 1 meter per second. The velocity works out to be 7.62 meters. That's our displacement. Divided by 10 seconds gives us a velocity of 0.762. However, that's complete velocity because it doesn't include the direction. So the last step would be use trigonometry to determine the angle of direction. We won't do that right now, but to figure out this angle of deflection, we would use some simple sine, cosine, tan types of trigonometry. All right? And that'll come up a little bit later.